Welcome to Study Loop.
This question concerns carbonic anhydrase. Metallic elements are essential components of many important enzymes operating within our bodies. Carbonic anhydrase, which contains the zinc 2+ in its active site, is responsible for rapidly interconverting dissolved CO2 and the bicarbonate ion. The zinc is tetrahedrally coordinated to 3 neutral nitrogen containing compounds, nitrogen containing groups, I should say, not compounds, and a water molecule. And our first order of business is to sketch this. Okay, what else do we know? A coordinated water molecule has a pKa of 7.5, and this is crucial for the enzyme's activity. Our first order of business is to draw the active site geometry. We're going to draw, and we're told to use N for the nitrogen containing groups. And this was a tetrahedron, so I'm not going to draw it super fancy here. Oopsie. That's zinc in the middle. I'm going to erase a little bit more so I can write zinc. And we could put our water anywhere. I'm going to put it right here. And then I put my ends here, here, and here. So there is A. B says, let me see what B says here. 92. Compare the pKa of the water molecule in the compound we just looked at, which was 7.5, to the pKa of pure water. Which species is more acidic? Okay, so we're going to compare the carbonic anhydrase to pure water. The pKa of pure water is greater than 15, and our carbonic anhydrase is 7.5. So the zinc central cation acts as a Lewis acid. And it helps stabilize the conjugate base of carbonic anhydrase. Zinc also highly polarizes the OH bond, even more so. And that's of the coordinated water. And since that bond is more coordinated, the hydrogen atom is more easily removed, making it a good donor. So the anhydrase is more acidic. Okay, now we have our next part. Hope it's our last part. It is not. C says when the coordinated water in the zinc 2 ion center is deprotonated, when the coordinated water, I should really go of right there, of the zinc 2 cation center is deprotonated. So that means it's going to lose a hydrogen. What ligands are bound to the zinc 2? And we're also told to assume the nitrogens are unaffected. The nitrogen containing groups are unaffected. Okay, so if our HOH loses that, we ended up with the hydroxide ion. What we're going to get is the hydroxide ion. I think that's all they're looking for here. And let me go find our next part of this. And what's D? Actually, there's E of this. Good heavens, this is a long problem. The pKa of blah, blah, blah. Okay, let me go to the next page. So we're given that the pKa of the compound or the ion whose formula I've written there is 10. And why the difference between this and the carbonic anhydrase? Okay. Okay, explain the phenomenon. So in the carbonic anhydrase, The zinc 2 is coordinated to the 3 nitrogen-containing N groups and 1 H2O. The N groups stabilize, I should write, the negative charge more than all waters. I think that's good. And last but not least, would you expect carbonic anhydrase to have a deep color like hemoglobin and other metal-containing protons? Explain. Let's go to a different color. Okay, so this one is pretty easy because the zinc compound, or the zinc 2 plus ion, has 10 d electrons. And since it has 10 d electrons, the dd transitions aren't possible. Because there's nowhere since it's full. So it's colorless. We're done.